find volume, then we will see then we will start a new section 12.8. Then let's start by one example. Then example find the volume, of the solid, find the volume of the solid that lies between x squared plus y squared plus z squared equals z, and z equal to root x squared plus y squared. Okay, so find the volume of the solid that lies between x squared plus y squared plus z squared equals z, and z equal to root x squared plus y squared. Actually, in section 12.3, maybe, or 12. Okay. Let me see any questions. So, guys, you cannot see. Mark, you cannot see. I keep getting booted from the chat room. Really? So, anybody else has a problem? Just Mark has a problem? You guys can see what I'm writing? So, okay. Mark, sounds strange. It seems that you are the only one who has a problem. That's strange. Oh. Okay. So, Mark, let's see actually if you can fix. Oh, I'm sorry. So, see, find the volume of the solid that lies between these two. Then see, this guy is a cylinder. Sorry, this guy is a sphere. This guy is a cone. What's the difference between this cone and cones that we have seen before? Here, center actually is not origin. The only difference is this. Here, if you want to find center of this one is because you can write this guy as y squared plus z minus 1/2 squared equal to 1/4. If it is strange for some of you that how did I get this, you just need to subtract both sides from z and use completing a square. But see, finding this equation is not necessary. The only thing which is necessary here to know is the shape of this graph. This graph actually is a cone. I'm sorry, is a sphere. And here we actually have a sphere like this, and we have a cone. And this guy is a cone. Then what volume must be found? Again, here we have to find the volume of the ice cream. Then if I want to be more accurate, I can say that we have a cone here and we have a sphere on the top. And our goal is to find this. Then this blue one is x squared plus y squared plus z squared equals z sphere. And we have a red cone. Z equal to root x squared plus y squared. Then our goal here is to find the volume of this solid. Actually, the solid that we have here, you remember the ice cream that we had before, again, same shape. And when I was solving that question, I told you when we see more technique, we will find this volume by using different technique. Actually, here we are using that technique. And see, you have a sphere on the top, you have a cylinder, a cone on the bottom, and your goal is to find the volume of this solid. Okay, so then let's see. I can say that volume of this solid equal, okay, let's denote this solid by E. By using the concept of triple integral, we can say that this volume equal to triple integral on E dV. I explained this before. When you want to use triple integral to find the volume, you need to write 1 here. Then here I wrote 1 here, 1 times dV is itself. Then this is E. What is E? E is this solid. So, okay. Yes. So then see, okay. See, on the top you have this equation. On the bottom we have this equation. Then here, then I want to find, if I assume that I will label the last integral by z, then I can find bound on the last integral very easily, because see, z here is given root x squared root, then we have 2 integral. The last integral has 2 bounds. On the bottom we have this one and root x squared plus y squared. Why? Because cone is on the bottom. What about on the top? Then see, on the top you need to find an equation for this. Then here you need to solve for z. If you want to solve this, you need to solve this guy for z. Let me see. Again, if you want to solve by z, as I told you, it can be written as x squared plus y squared plus z minus 1/2 squared equal to 1/4. Then you can make z alone here. Then if you make z alone here, you have z minus 1/2 squared equal to 1/4 minus x squared plus y squared. Then you have z minus 1/2 equal to plus minus root 1/4 minus x squared plus y squared. See, okay, it is clear that if we solve this equation in Cartesian coordinate, we need to deal with such a horrible function like this. That's actually something very hard, and I don't want to do something like this. One more time, then see, if you want to solve this volume in Cartesian coordinate, you assume that the last integral is labeled by z. Then you need to find bound for z. Finding lower bound is easy. Why? Because z here is given alone. Then you can write this as the lower bound. But when you want to write upper bound on the last integral, you need to make z alone here. And unfortunately, making z alone here is not easy. You need to use completing a square, get this, and after that you need to solve this equation for z. And actually the equation of something that we have on the top is z equal 1/2 plus root 1/4 minus x squared plus y squared. That's a horrible function, see? Okay, then solving this equation in Cartesian coordinate will give us this horrible function, and I want to escape of using this horrible function. That's a horrible function. Then it seems if we convert this integral, if we convert this volume into a spherical coordinate, we can solve this equation easier. Someone can ask this, Ali, how do you know that here we need to convert to a spherical coordinate? Because cone and the sphere are given. Cone has a nice equation in a spherical coordinate. Sphere also has a nice equation in a spherical coordinate. Then here converting into a spherical coordinate can be very helpful. Any question? Any question? Question? Okay, so then I prefer not to use Cartesian coordinate. Then let's erase these. I just wanted to, okay, these stuff are not part of solution. I just wanted to tell you why Cartesian coordinate here doesn't work. So, see, we have x squared plus y squared plus z squared equals. So, let's convert these two equations into a spherical coordinate. We converted this equation into a spherical coordinate before. Some of you may remember the equation of this guy, phi equal to pi over 4. Here we have phi equal to pi over 4. That's easy. What about this guy? We need to convert this equation also in a spherical coordinate. And let's do it. Okay, as I explained before, x squared plus y squared plus z squared can be replaced by rho squared. Then x squared plus y squared plus z squared can be replaced by rho squared. Equal to, what about z? Again, as I explained before, this is rho cos of phi. Any question? Let's see, this is the formulas that we had before on Monday, I think. X squared plus y squared plus z squared can be replaced by rho squared. Z can be replaced by rho cos phi. You can simplify rho because rho is not 0. Then you have rho equal to cos of phi. Then the equation of this guy, the blue sphere that we have on the top, is rho equal cos phi. Then see, I converted both equations into a spherical coordinate. The equation of a sphere that we have on the top is rho equal cos phi. The equation of a sphere that we, I'm sorry, the equation of the cone that we have on the bottom is phi equal pi over 4. Any question? Any question? Okay, so this is z-axis, this is y-axis, this is x-axis. And we have x squared plus y squared plus z squared equal 0. Any question? Let's see, I converted both equations into a spherical coordinate. For this guy, you have phi equal pi over 4. For this guy, you have rho equal cos phi. So, now we are ready to find this integral. And let's do it. See, we don't need to write something as z, x, and y. As I explained before, if we want to solve this in spherical coordinate, the last integral is labeled by rho. Okay. The last integral is labeled by rho. The second integral is labeled by phi. And the first integral is labeled by theta. Rho, phi, and theta. Rho, phi, and theta. Any question? Any question? Any question? Actually, the shape that I drew here is a little bit wrong, right? Because we have, sorry about that, sorry. I think it should be, sorry. It should be here, right? Okay. Right, because and let me see, yes, for a sphere, actually, this one is on, and then this is y-axis, this is, I'm sorry, this is x-axis, this is y-axis, z-axis, yes, no, it's good. And any question? Okay, everybody's following what I'm doing. I'm saying that, see, this origin cannot be here. Origin actually must be here. Why? Because the cone actually is passing through origin. But the center of this cone, I'm sorry, the center of this sphere is on z-axis. This is center is on z-axis. Center of this guy actually is 0, 0, 1/2. This is the center of this sphere. Therefore, this is on z-axis. This is on the z-axis. Okay. Any question? Any question? Any comment? Anything? So then see, I converted this. Okay. Again, I want to make sure everybody's following. Then see, you have a cone on the top. You have a sphere on the top. You have a cone on the bottom. I converted this sphere into spherical coordinate. Then I got rho equal to cos of phi. After that, I converted this cone. Actually, I converted this cone before into a spherical coordinate. Then we got phi equal pi over 4. Phi equal pi over 4. Any question? Any question? So, you know what we should do? We need to understand the intersection between these two surfaces. Here, see, you have a sphere, you have a cone. On the top, you have a sphere. On the bottom, you have cone. You need to understand the intersection between these two. Actually, this intersection here is very important. Then let's find intersection. Then, okay, can I erase here? Okay, so then let's understand this intersection. You have x squared plus y squared plus z squared equals z, and you have z equal to root x squared plus y squared. See, you have your goal actually is to find the intersection of these two. Then you have x squared plus y squared plus z squared equals z. When you want to find intersection, it means everywhere that you have z, you will replace z by this guy. Then let's do it. We have x squared plus y squared plus, here we have root x squared plus y squared plus root, equal to root x squared plus y squared. Question. So what I'm doing, my goal is actually to find the equation of this. And since I want to find the equation of intersection, then here we can say z equal root x squared plus y squared. Here we have this one. Then everywhere that I had z, I replace z by this one. So then these two and root 2, they cancel each other. Then you have x squared plus y squared plus x squared plus y squared equal to root x squared plus y squared. You have 2x squared, you have 2y squared. Then here it can be written as, okay, so let's see, 2, no, that's bad. Then we can, no. Guys, let me delete this one. Then we can say 2x squared, 2y squared equal to root x squared plus y squared. Any question, please? Any question? See, do we see actually what's happening here? I try to solve this equation in a spherical coordinate. I'm sorry, I try to solve this equation in Cartesian coordinate. Here, as you could see, I reached to something horrible. Then why this happened? Because you are trying to solve this in Cartesian coordinate. And as you can see, you got really, really hard equation. And here again, we need to take a square, both sides, then simplify, blah, blah, blah. And at the end, only God knows if we can find a final answer or not. But what about if we use Cartesian, if we use a spherical coordinate instead of Cartesian coordinate, if you use the spherical coordinate for this guy, you have rho equal to cos of phi. What about this guy? For this guy, you have what? You have phi equal to pi over 4, right? Right? Then see, then when you want to find the intersection, you just need to plug in phi here, pi over 4. Then see, instead of solving such a horrible stuff, we can solve much easier. Then see, this is horrible. But if you write this in a spherical coordinate, you just need to plug in pi over 4. Then you have rho equal to cos of pi over 4, which is root 2 over 2. That's it. Any question? Any question? Any question? Then see, here you have, this is the equation of this guy, rho equal cos phi. We found this before. For this guy, we have phi equal pi over 4. Then here, when we want to find intersection, we just need to plug in on the top. And when you plug in on the top, you get cos equal pi over 4. Then you have rho equal root 2 over 2. Any question? So then this is a bound that we need for rho. Then we have root 2 over 2. We have cos of phi. For phi, again, I got here root 2 over 2, and we have cos of phi. For this guy, we have pi over 4, pi over 2. For this, we have 0 to pi over 4, pi over 2, 0 to pi, and root 2 over 2 cos of. Here we need to write also Jacobian. Jacobian here is rho squared sine of phi d rho d phi d theta. Rho squared sine of phi d rho d phi d theta. Okay, finding this, I'm sure that is easy, all of you can do it, but the only thing actually here which was important is finding bounds here. As you can see, finding bounds for pi over 4, pi over 2, because this guy is pi over 4, then we have pi over 4, pi over 2, then here we can plug in there. And after that, we have these two cos of pi, then root 4 this, and pi. Any question? Any comment? Any question? Okay, so, okay, then I just wanted to write this, then that's a good question to see that actually what we can do. Then again, see, when you want to solve something like this, then when you want to find intersection, then intersection between them, see, we need to use this equation. Then if you want to solve this equation, you need to take a square both sides and solve it. That's exactly a hard question.